Hi guys, in this video we will try to get answer to this question. What is the expected value of the sum of two dice, six-sided? And let us assume then whenever we talk about a die, we are talking about a fair die. Okay, so let us assume that both the dice are fair. We will import these libraries. Now, what is this? Let us run and see. It has created this data frame. What we have done, this is list comprehension. We have generated 1 to 6 number and we created a data frame for those numbers 1 to 6 and we named index from 1 to 6, 1, 2, 3, 4, 5, 6. Then columns, which column? For 1 to 6, we named column as RV, that is random variable. What is frequency for each and every random variable? If a die is 1, 1, 1, 1, 1, 1. Probability 1 by 6. And expected value? Well, we know for expected value, we have to multiply random variable by its probability. You will get expected value. So for random variable 1, the expected value is this much, and for 2, this much, so on so forth. When we sum this column, we will get 1. But when we sum this column, EV, we will get 3.5. Now, this was all about single die. We are talking about one die. So we created a data frame. We have done everything about it. But the question is about two dice. So let us transport our knowledge of one die to two dice. Nothing will change. One additional die is going to come and we have to deal with two dice. So we will try to create this sort of table for two dice. First of all, let us discuss some fundamental things about two die. See, we have created this list comprehension. So let me discuss each line in detail. So here, let me make room for this. Okay, let me bring this here. This is list comprehension. What we are doing for I in range 1, 7, and this is within bracket. That means we are trying to make double dimension and we have outer bracket for j in range 1, 7. So what is happening here? We know list comprehension very well. So for j in range 1, 7, 1, 7, j is 1 and j comes here. It remains 1 and this loop has to be over. This I will be 1, 2, 3, 4, 5, 6 and j remains 1. So we have first row 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6 because we have written j first. So 1 is first in this tuple of two numbers. Next, j becomes 2. So j will be 2. Again, I will start 1, 2, 3, 4, 5, 6. So 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. So on so forth till 6. When we have done this, if we count, we will see there are 36 distinct combinations, unique combinations. 6 into 6, 36. And for this combination, we have created a data frame. So let me delete this. Okay. Having created data frame like this, we have given index name like this. What is that? D1 denotes die number 1. And what is 1, 2, 3, 4, 5, 6? All the numbers of die 1. And what is the D2? Die number 2, second die. So D2, 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 D2. Again 1, 2, 3, 4, 5. So these are column names and these are row names. And we have first row like this, second row like this, third, fourth, fifth, sixth. And if we have to talk about column, this is first column, second column, third column, fourth column, fifth column, sixth column. Great. Now, see, the question is interested about sum of two dice. It is not talking about what numbers are involved. So what we will do, we will try to sum these two numbers, 1 comma 1. We will add them. It will become 2. And see, 1 comma 2 will become 3. And this 2 comma 1, this will also become 3. And then see, 3 comma 1, this becomes 4. 2 comma 2, this becomes 4. 1 comma 3, it becomes 4. And all this will become 5, then 6, then 7. So let us see that what is going on here. We will now just see in the list comprehension, we earlier wrote j comma I. Now we are saying j plus I. So what will happen? Everything remains same. Instead of 1 comma 1, we are getting 2. 1 comma 2, we are getting 3. 2 comma 1, we are getting 3. Okay, great. Now we have 36 numbers. Some of the numbers are now repeating. Here we said all are distinct combinations. Why? 2 comma 1 is not what 1 comma 2 is. They are two different things. But if I sum these two numbers and this also, both of them will become 3. So that is what is happening. So now let us see what has happened here. See, we have 1, 2 in 36 boxes or cells. There is only 1, 2. There are 2 threes. There are 3 fours, 4 fives, 5 six, 6 sevens, again 5 eights, 4 nines, 3 tens, 2 elevens, and just 1 12. So this is what this data frame is talking about. It is just this one and this. These two data frames are fancy representations of the values when we roll two dice. Okay, this is showing some of the numbers and this is showing various combinations of numbers involved. Good. So that's it. The purpose of these data frames is over. We don't need these data frames anymore. Now let us get to the point. Let us calculate expected value of all possible outcomes, that is sum, from the roll of two dice. And this data frame is telling us that, look, when we roll two dice, we may get 2, we may get 3, we may get 4, we may get 5, may get 6, 7, 8, 9, 10, 11, 12, fine. But for these numbers, probabilities are different for each number. Look, when we had single die, every single number has same probability, that is 1 by 6. However, when we have two dice, the probability of getting 2 is 1 by 36. There is only 1 2 out of 36 numbers. And what is the probability of getting 3? 2 by 36. What is the probability of getting 4? 3 by 36. For 5, 4 by 36. So on, so forth. Again for 12, it will be 1 by 36, and for 11, 2 by 36. That is what we are going to work on. So what we are doing now, here we have created this data frame fine. Now we are again generating the same set of numbers and putting in a variable called x. And let us see what x shows. See, x over here holds these values, all these values. And what will be length of this x? It will be 36. Let us take that length. Oh no, len. Okay, so long list. Fine. So let us save some time, save some space by seeing only 4 numbers. Okay, we know that it has got 36 numbers. Now, for this x, we know 2 is 1, 3 is 2, and the frequency of 4 is 3. So we are creating a dictionary. By creating a dictionary, we can very easily see which number's frequency is what, rather than looking in this particular data frame. So 2 is 1, 8's frequency is 5, 9's frequency is 4, and 12's frequency is 1. So all the numbers have got their frequencies. Now what we'll do, we can make a bar chart. It is of no use, but just it is very nicely representing this information. Here we have key value pairs. Here we have graph. Same data. What is going on? See, 2 is 1. 3 has got frequency 2, and 4's frequency is 3. 5's frequency is 4, and 6's frequency is 5, and 7's frequency is 6, so on and so forth. Again for 12, the frequency is 1. So if somebody is interested in picture, this picture can be seen, this graph can be seen, or else anyway the information is very much available in this dictionary. Done. Let us move forward. Expected value of a 6-sided die. How do we calculate manually? We did earlier. 1 multiplied by 1 by 6. Random variable, that is 1, and its probability 1 by 6. Random variable 2 multiplied by its probability. Every probability will be 1 by 6. That is 0.166667. So when we do that, we get 3.5. We do manually calculate. Correct? Which we have already done. I mean, have we done that? No. Yes, we have done this. Look, here we created, right? We saw 3.5. See, the total of this is 3.5. This is what we are doing there. We are doing here manually, and here we created a data frame, and it looks much better, right? We have random variables, we have each and every random variable's frequency, we have each and every random variable's probability, and then expected value is derived, and then when we total this column, we will get expected value of a single die, 3.5. And when we total all the probabilities, total probability will always be 1. 0.999999999 should always be considered as 1. Okay, so this we have already done. This is manually we can done. We have done this. Now this knowledge will be handy when we will deal with two dice. See, expected value of the sum of the two numbers obtained when two dice are rolled. Here, when a single die is rolled. So, in two dice, what will happen? See, we will never get 1. We will get the minimum number is going to be 2 because minimum number in each die will be 1. And when we are rolling two dice, if both the dice are showing the minimum number, it will be 1 and 1. It will be 2. The sum will be 2. So 2 being the least number. And what is the probability? 2 will appear only once. See here, 2 will appear only once. Hence, the probability is 1 by 36. What we do? We always multiply random variable. What is random variable here? 2 is random variable. Multiply by its probability, 1 by 36. And 3, what is the frequency of 3? 2. So 3 multiplied by 2 by 36. 4, what is the frequency? 3. 4 multiplied by 3 by 36. So on, so forth till 12. And what is the frequency of 12? 12's frequency is 1. That means 12 will appear only once. Then 12 multiplied by 1 by 36 because there are 36 numbers, right? So once we do this and try to look this, it is going to be 7. For 1, the expected value was 3.5. Accordingly, without changing any logic, just include another die and do the math, we are going to get 7. So this we have calculated. We have discussed this n number of times that we are not going to get the numbers in this fashion. It is not that 36 times if we are going to roll two dice 6 times, we are going to get this combination. It is not going to happen, right? It is just not going to happen like this. These numbers will not appear. Some numbers will appear more number of times and some numbers will appear less number of times. But then we always know how to use the law of large numbers to get to the conclusion. That we will do. But this particular calculation is very manual and we have to type a lot. The same thing has been done here. What we are doing here? We are getting 7, but what is going on? So let us just see. We have created this key, right? D is nothing but dictionary. So let me make some room and let me explain what is going on. This is D. This is dictionary. When we say keys, we get only the random variables. Correct? Now, we cannot say multiply by 2 all the numbers. If at all we want to do that, it will not allow. What we have to do? We have to convert this into an array. So if we try to convert into array, it will not. Will it convert? See, it is coming array, dictionary, then we'll say multiplied by 2. We are getting error. So listen, what we will do is, we will not directly convert into array. We will say, please convert into list. Okay. Now, if I say 2 multiplied by 2, suppose we want to multiply all the numbers by 2. So It is not multiplying. In fact, this list got doubled. If see I multiply by 3, the list got tripled. So that is not the idea. We want to multiply each and every number inside this key by 2. To do that, let us convert into this list into array. Now we say, if we multiply 2, what will happen? 2 2 ja 4, 3 2 ja 6. It will start happening. See, 2 2 ja 4, 3 2 ja 6, like that, and 12 2 ja 24. So we are not going to multiply by 2. That was just an example. What we will do, we are going to multiply by the probability of each and every number. Listen, what is the probability? Let me bring the original number. Okay, 2, 3. What is the probability of 2? 1 by 36. What is the probability of 3? 2 by 36. From where I will get? Let us talk about the frequency. D values. What does it contain? It contains the frequency of each and every number. So 2's frequency is 1, 3's frequency is 2, 4's frequency is 3, likewise 12's frequency is 1. So we will divide this. If we divide by 36, is it going to happen? We have problem. We have to convert into array. So even list is not going to help. We have seen earlier, right? We will divide by 36. It doesn't help, right? So let us convert this into NP array. Now we will say multiply by 36. Will this happen? Oh yes, it will happen. So now we will bring this. Let us put comma here and just see how it looks. This is how it looks. Let me remove this. Okay, let me go slow and let us understand every small piece over here. So this, now I want to multiply by this. Why? Random variable 2's probability is 0.0277 and random variable 3's probability is 0.055. That is 2 by 36. This is 1 by 36. Okay, so let us remember, what is this? 2's probability is 0.027, 3's probability is 0.055. Likewise, 12's probability is again 0.027. We have already calculated the probability for each and every random variable. Have we done? Okay, we are doing. After this, we will be doing. So let us multiply this. Okay, 2 multiplied by this, 3 multiplied by this, 4 multiplied by this, and 12 will be multiplied. When we do this, what will happen? Okay, we got expected value for each and everything. Now what we will do? We will say sum. We got 7. Okay, so this is too much of work, correct? And it is not very transparent what is going on. Yes, things have happened, but to let things appear in a very nice way, what we can do, we will create a data frame in line with this data frame. This data frame is calculating individual probability and expected value for a single die. Now we are creating a data frame which will show us each and every random variable's probability and expected value. So let me run this and we will get into details. See, we have this 11 numbers, 2 to 12. What is the frequency of 2? 1. 3's frequency 2. Okay. If it in doubt, we can always go back and just see these things. right? We created dictionary, correct? Now, all this frequency are there. The probability of random variable 2 is what? 1 by 36. This is 1 by 36. This is 2 by 36. This is 3 by 36. Correct? And what we do to get expected value, we multiply the value of the random variable, each and every value of the random variable, by its probability. So what is the probability? This. And what is random variable 2? So I'll say 2 multiplied by its probability. That is 1 by 36. Whatever we get, that is called expected value. 3. And what is the probability? 2 by 36. This is 2 by 36. Now multiply random variable 3 by probability, its probability. We get this. We will continue like this. When we take the total of this expected individual expected value, we will get total expected value for 2 dice. Okay. So, and when we total this column probability, we will get 1. These are all individual probability, and this is expected value for each and every random variable. So let us run this and just see. This is 1 and this is again 7. Look, we already calculated like this 7. We also calculated like this. This is one way. This is a very crude way of calculating. This we are using, but too much of syntax, right? Too many parentheses, etc., etc. Convert into list, then convert into array. This is, yes, it does take time, but it is crystal clear. Anybody can read and understand what is going on. And the command is what? Create data from for keys, D keys. What is D keys? D keys is nothing but, see, D, 2, 3, 4. Create data frame. We will call that as random variable. This column got created. Frequency is what? We already have in our dictionary frequency. We'll take 1, 2, right? Those are frequencies. D values, they are nothing but frequencies. We will populate this column. Probability is what? Frequency divided by 36. Correct? 1 divided by 36, 2 divided by 36, 3 divided by 36, 4 divided by 36, so on and so forth. Then EV, expected value. How EV is calculated? Random variable multiplied by probability. Random variable multiplied probability is giving us expected value for each and every random variable. And then cumulative sum expected value. This is nothing but we can total and get 7, but we can also step by step total, right? That is nothing but cumulative summation. This comes here, and then this and this gets total, we write here. Then 3 gets total, you write here. 4's total here, 5's total here, so on and so forth. Then all 11 numbers total here. So if I see the last value, that is nothing but expected value. Either we can sum this or we can see this individual cell. Good. So we are doing the same thing in many different ways. Let us move on. Now that we have this X, remember we created this X, right? There's nothing but all the random variable, 36 numbers. Of course, different number has got different frequency. Now, what we'll do? We will start simulation. That X, that 2, 3, 4, some of them would be repeating till 12. We will start treating that X as source, and we will collect 100,000 numbers from that X and put in RV, a variable. And then we will create a data frame with that variable and name that data frame as df underscore RV. And the column name will be RV, that is random variable. And then index, we will make 0 as 1. So the last number will always be length minus 1. That becomes equivalent to length. So we will just write plus 1. So no 0 business. Okay. Now we will, having created that, we can always see this data frame. It is going to be very, very long, right? How many? 100,000 rows. This we did earlier as well. Now we are creating dictionary for all these variables. Look what is going to happen here. If I say RV, see what is happening? We are creating dictionary and saving this variable. So the 6 got selected 13,878 times, and these are all jumbled, right? Let us see this in a sorted manner. There is a way to do that. Sorted DRV items. Now 2 to 12, 11 numbers, and look at the frequency. Which number will get selected most of the time? 7. Maximum number of times 7 is getting selected. Why? Because its probability is highest. Which two numbers will get selected the least number of times? That is 2 and 12, and it is very much evident over here. Okay, 2645, 2732. Fine, very good. Now some DRV values. What are we doing? Look, all these values should sum up to 100k. Just verifying. Yes, correct. Good. Now we will say draw histogram for that 100k numbers and make 11 buckets or 11 bins, and it will look very nice now. What is happening? See, this 7 number has got highest vertical line because it got selected maximum number of times. See, 16,731. And then comes the turn for 6 and 8. Look, 6 and 8 are second most frequently selected numbers, so on so forth. This particular graph is representing which number is getting selected how many number of times. So each number is getting dictated by its probability, and that happens only when we apply the law of large numbers. So selecting 100,000 times is nothing but deploying the law of large number in our logic. So this is what is happening. Very good. So far so good. So let us now next simple thing. Let us see our data frame once, how it looks. Our data frame DFRV looks like this. Only numbers. It has nothing other than random variable. Now we will start populating. What we will populate this with? First will be is 2, is 5, is 4, means column name itself will be a question mark. So what will happen? If the random variable 6, we will create 11 buckets. In 6, we will put a count as 1. If it is 7, in the 7th box, we'll put not 7th box, the box with the name 7, count will be 1. 8 again. So let us run this and we will discuss. DFRV. Let us only concentrate here. Let us not see there. See here. Is 2. No, no. Random variable is 6. Is 6? Yes. Put 1 here. We are basically counting numbers. 7 under 7. 8 under 8 put 1. 6 again 1 has come. 4 under 4. And we also have other column. Let me do this again. If you see, we'll get all the list. Yeah, good. So basically this particular command, we are saying that please show us 40 columns. Okay, just written 40. So all the columns we can see. Otherwise it will hide. So see what is happening. Next, what we will do? Cumulative sum. CS stands for cumulative sum is 2. Look, let us talk about 6. See, 6 is appearing twice, right? Here itself. So 6, what will happen? Cumulative sum is 6. 1. 6 is not there. 1 will continue. Here also 1 will continue, right? And look, in the fourth row, 6 has again come, which means cumulative sum of 6 will become 2. It will continue with 2 unless and until it finds the third one. The moment it finds, it becomes third. See, we have done this several times. It is just a repeat over here. So we are doing cumulative sum for each and every random variable. Okay, then what? Having done that, we are calculating expected value for 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. What we are doing? This time it is little different. Cumulative sum, we are multiplying by RV, random variable, and dividing by the index number. Why so? So let us go and see this. What we will do is, when we are counting this number, it is coming, right? So as 2 has come, random variable 2 will come. We will take a count sum, right? We are going to multiply by random variable every time and then divide by the index number. Earlier, in one die, there was no problem because every number's probability was same. Hence, we were simply multiplying by we were not multiplying with anything. We were simply dividing by index. Now we have to multiply by random variable. Okay. Now, when we do that, we are going to get expected value for each and every numbers, and then we will check. Oh, this is fine. This we have already seen. And what are those columns? These many columns are there. Look, is 2 to is 12. Cumulative sum is 2 to cumulative sum is 12. Then expected value 2 to expected value 12. 3 set of different columns. Okay. Is takes the count, cumulative sum, it sums up cumulatively, and EV calculates expected value. Then, since we are only interested in EV, we are storing this EVs. And let us head only these tail bottom 5 rows, and there is no need to see this. If we are interested to see only this, what will happen? Okay, EV we don't need. So EV is nothing but the expected value data frame. This we don't need here. Let's eliminate. And here we are generating charts now. For first 100 roles, then for first 1000 roles, then for first 10,000 roles, and then for all the roles. We will create this and just discuss what is going on here. See, there are 11 lines. And what are these dash dash line? For 2 to 12, the expected value. So just see, it is going to slowly settle down. This was 100. Now this is 1000. So till this 1000, we were seeing here. Now we are seeing till 1000. Then till 10,000 and then till end. When it is ending, it will get aligned to all dash dash lines. Now, what are those dash dash lines? See here. Those dash dash lines are expected value for each and every number. Remember this, what we are writing here. Expected value. We are taking from DF, EV, RV. That is nothing but for 2, what is the expected value? So let us take this, and that is precisely why probably it was written DF, EV. What is the expected value for 2? 0.055. See, there are 11 lines. It is very difficult to uh, find out where our random variable 2 is falling, but for that it should be 0.055. And let us talk about the most frequently occurring number, that is 7, and its expected value should be 1.16. So look here, 1, and the topmost line belongs to our random variable 7, and the least will be belonging to which one? 2 and okay, not 2. Let me see. Yes, it is 2. It is 2. Okay. So what is happening here? We have legends also, 2, 3, and all those things. 7 is got dash dash. So, but we don't have distinct colors, so we cannot really correlate very well. But the idea is, initially, it is going through too much of turbulence, but because of the law of large numbers, all the respective probabilities will be seen. So all these expected values which were having a lot of turbulence initially got settled with their respective probabilities. So that is why we have drawn this dash dash line. See, these dash lines are there and these lines are not at all coming on top of that. They took some time, some more number of rolls to slowly settle down. Just see, settling, but it's still a little bit of waves, right? And all those waves will go off now. Almost got straightened. So this is nothing new. We did check this for single roll, and this we are doing for, earlier we saw for the roll of single die. Now we have checked for the roll of 2 dice. So is there anything left now? Okay, now what we are doing here, we are saying, okay, just see what is going on here. When we see tail, this is the last. If we total, we should get 7. How? Just see. We'll say, do one thing, convert into values. Okay. Then we'll say take 0. See, this double brackets are there. So we'll take. Now it is there. Now we will say, please sum it up. We got 7. What is this? Let me repeat. See, when we are saying DFRV, when we are saying tail, only one record is the last record. See, last record, what will happen? This EV, this last is nothing but the final probability for each and every number. Correct? So that is what we are taking values is giving only values, and then we are summing it up and we are getting this. Only for verification purpose. So this graph is about individual expected value for 2, for 3, 4, 5, so on till 12 individual. So all these individual expected values, if we add, we will get total expected value. Correct? See here, individual expected value. If we total this, we will sum this up, this column, if we sum, we will get total expected value. And that is what we are doing. Correct? Okay, that is done. And what is this? Okay, now rather than doing like this tail one and all these things, we can also do little systematically. See, these numbers have come. So what we are doing, df underscore rv column apply lambda x sum x. When we are doing, we are getting one series, and then we can take the sum of this series and divide by the length of our data frame. So what we'll get? We'll get 7. Same, see, this is 7, this is 7. I mean, these are all different ways of getting the expected value. Yeah, it is a bit complicated. I mean, we have written too many lines, and we have discussed a lot. I hope it is clear. Thanks for watching, and I will see you in the next video.